Hello, everyone, and welcome to my presentation. So my name is Antoine Salgas, and I'm a PhD student right here in Supero, and I'm working in ISE as well, the Institute Laurent presented earlier, as a way to extend our activities to several other sectors other than aerospace engineering. And in particular, I'm working with business school, Toulouse Business School, to extend our models to economical activities. But that's not what I'm going to talk about today. I'm going to talk about a project I've been doing while I was a visiting scholar in TU Delft with Junzi last spring, about compiling and an open source traffic and CO2 emission dataset for commercial aviation. So I will go to several points today. First, I will explain our context, what we are doing in our research team. So it will lead us to understand why I've been doing this work. Then I will dive into some more details about this specific work and about the data we chose. Then we'll evaluate the resulting dataset, the compiled dataset, and then I will show you a little tool to facilitate the data visualization that I've been developing before concluding. So to begin with, we are a team working on prospective scenarios for the decarbonization of air transport. So what is a prospective scenario? It's looking at the possible futures for the decarbonization of aviation, looking at the different options. Several actors have been doing this, such as academia, industrial or institutional actors. And there's no common framework to compare those different scenarios. So what we are trying to do is to compare those different scenarios, to build our own scenarios, having an as broad as possible approach, including technology, sociology, and economy, among other fields, into the study. That led to the development of aeromaps, which was formerly known as CAST. Maybe some of you heard about it with this name, which is an open source framework that allows us to perform multidisciplinary assessment of those prospective scenarios using Python and Jupyter Notebooks for advanced users, and also this interface that is currently under development and will be available very shortly under, I guess, 1 or 2 weeks online. So the fact is, right now, aeromaps is only available for worldwide analysis, and a feature that was requested by airlines, airports, and government was to be able to refine the analysis. For example, to be able to do the decarbonization strategy of Europe or France of a given airport. But that meant that we have to switch from the current top-down approach for estimating CO2 emission that is just looking at the fuel consumption, the kerosene consumption of the whole world, to a much more bottom-up approach that computes each fuel burn for each flight in the world, for each route at least, not each flight, but so that we are fully able to partitionate the estimation as we wish. The problem is there are no such open source database, or there are commercial database that allows us to do this, but nothing in an open source friendly context, meaning that we would have to restrain very much the reproducibility of our research. That led us to try to do this work by ourselves and to compile an open source traffic and emission dataset, which is what I'm going to explain in this next section. So I will give you an overview of the methodology I've followed in the last in this work. So the starting point was to use the existing available open source datasets, such as the United States BTS dataset, OpenSky dataset, of course, Eurocontrol R&D dataset, World Bank dataset, and Australian and Brazilian national datasets. Then we can aggregate these datasets to extend the coverage as much as possible using those existing open source datasets to have a broader open source dataset, but we are still missing some flights, for instance, in Asia, which is not covered at all by these datasets. So that led us to consider an alternative option, which is to use Wikipedia airport pages. I will explain later, but using this dataset, we're still missing the traffic information on the existing routes. We know there's a route, but we don't know if there's 10 or 1,000 flights per year on this route. So at this moment, we thought about using, once again, the open source traffic data you see above here to train an estimation model, a traffic estimation model, using social, economical, and geographical parameters, features to train this model, so that afterwards we can use this model on routes in which we don't have any traffic information to estimate the traffic on those routes. And finally, once that is done, we are able to compile it back with the open source traffic data I've talked about earlier to have a broad and complete coverage data set. And in the process, we are also able to estimate the fuel burn and the CO2 estimation. So now I will dig into more details. So the starting point was really to focus on the existing traffic data sets in here, which you can see have very different characteristics. We are focusing at the route levels. That's something quite important for here, because most of the data about the research about Open Sky Network focus on the detailed trajectory. We are just looking at the origin and destination route without looking at the 4D trajectory. And depending on the data set, sometimes the aircraft type is included, sometimes the airline is included, sometimes it isn't, sometimes the payload is included, sometimes it isn't, etc. But even with the compilation of all these data sets, the coverage is still incomplete. So using Wikipedia a lot for my personal purposes and reasons, I saw that each airport page of Wikipedia was indeed very using a very common structure, which each airport having an airline and destination section with every airline and every destination served by this airline with a type of link, if it's a regular, seasonal, or charter link. So it's relatively easy to gather all the URLs of airport pages on Wikipedia and to parse them using Python and a dedicated HTML analysis library such as Beautiful Soup to transform this Wikipedia database into a much more structured database with an origin, destination, airline, and type of relation structure. So the database is really decentralized and has been gathered using these automated Python scripts, but we still miss the traffic information. We don't know the traffic at all on each route. So to do that, we can add some features to each airport, some to try to train a model. So the first kind of features we can add to this previous database are geographical data. The first one that came to my mind was to look at the population surrounding each airport, the origin and destination airport, using a contour dataset, very extended open source dataset. We can also look if an airport is surrounded by other airports. For instance, Paris has 2 airports, so the Paris traffic is divided in those 2 airports. We can look at the size of the country, if the country is an island or not, and obviously at the distance between 2 airports, because that's an obvious link that will influence the traffic on this route. Then we can look at the airport information using Wikipedia once again, because on each page of each major airport, you have the traffic information, like the passenger traffic, the totals passenger traffic figure for each airport each year. So that's a very interesting things to include in our model as well. As in the previous slide, we are also able to count how many airlines are on each route, meaning that we can have an estimate if there are several airlines on a route, that it's a good information on the route importance or not. And the last category of features that I've included are more socio-economical data, so such as the GDP per inhabitant of each country. The Gini coefficient, which is a coefficient that measures the inequalities in a given country. We also looked at the tourism flow, because everything being equal, a country with a lot of tourism is more susceptible of having a lot of flights. We also look at the Human Development Index and most importantly at the trade flows between each pair of countries in the world. And those data are fully open source and made available mostly by the World Bank and also by the United Nations. So once all this data is merged on the Wikipedia parsed root database, we can use it to split this data if this database, if the root is also present in the open source database I spoke about earlier, or if it's not. If it's in the open source database, we'll use it to train an estimation model. And if it's not, to the estimation model will be used to estimate the number of seats. And in the end, around 60% of the roots of the Wikipedia parsed datasets were also included in an open source dataset, meaning we have to estimate the seats for 40% of these roots. We tried several different methods to regressors to estimate the number of the traffic on each route. And something I've not mentioned is that we are looking at the seats available per route, because that's something that is more interesting for us rather than the passenger information, because it's more related to the number of aircraft flying on the route, because there's a load factor that goes in between. We tried to use simple methods in the beginning, such as multilinear regressions, using regularization techniques, log linear regression as well, but these failed to provide a sufficient level of fidelity on the testing dataset. And in the end, we end up with more elaborated regression methods, such as normal random forest and XGBoost algorithm. In the end, we chose to use XGBoost because it features a relatively interesting R-square of around 0.6, depending on the test train split. And also something very interesting for us is that it allows us to have missing features from some airports, because not having a features is already an information in itself. If the airport is pretty small, it's more likely to have missing features in the various data that I've spoken just earlier. And then once the data is estimated, the traffic is estimated on those routes, we are going to aggregate the final data set, starting each time with the open source data. It's always more interesting to have those open source data that are real data than estimated data. We are going to consider only one kind of source available for each route to avoid duplicates and double countings. And in the last resort, if the route is not present at all in the open source data, then we use the estimated data. And an additional step was performed after the XGBoost regression. That was to use, once again, Wikipedia airport passenger traffic information to scale the flights going to and from this airport to minimize the residual of passengers, of the seats or passengers arriving to this airport. And in the end, if you look at the repartition of the different sources in the final dataset, we have around 5.5 billion seats, while the United States BTS source covers 1.3, Eurocontrol dataset 1.3, and the estimation dataset 1.6, while the World Bank dataset covers around 800 million seats. And that's being done. We still have to figure out a way to estimate the CO2 emission and the fuel burn. And to do that, I've used the Seymour surrogate that was mentioned in the previous presentation, because it's very simple for our use case and relatively reliable. It has a limited bias. And it just requires knowing the distance of each flight, which is something I know, and the aircraft type, which is something I know in some of the datasets. So there's two options then. If I know the aircraft type, I'm using directly the Seymour surrogate. And if I don't know the aircraft type, I'm just doing a simple regression on the previous flight that were included in the Seymour dataset, and to just estimate the fuel burn according to the flight distance. Now I'm going to evaluate and to present you some results about the dataset accuracy. So I've used three comparison sources. The first one being International Energy Agency total kerosene consumption per country. Then OAG dataset and OAG dataset, I guess most of you know that is pretty expensive data. So we had only 2018 datasets, while our work was conducted on 2019 to avoid COVID effects and to use the most recent year without the COVID effects. And to convert data from OEG from 2018 to 2019, we just use a uniform growth rate, which is a very obvious limitation. And the last source we used was ICCT dataset for CO2 emission and RPK that is gathered at the aggregated at the country level. We will evaluate this the dataset accuracy at the global, at the country, the airport, and finally at the route level. Because we have to keep in mind that our goal is really to focus on large flows, continental flows, for instance, country flows, but route by route estimation is not the main goal of this work. So really, this slide is where we wanted to validate the accuracy of our open source dataset. So if we are looking at the seats included in both datasets, we can see that this work underestimate by around 3.9% the total number of seats present in the OAG dataset, while in terms of available seat kilometers, so just multiplying the seats by each flight distance, we are overestimating by around 1.6% the OAG dataset and by 1.3% the ICCT dataset. And in terms of CO2, we are at a constant perimeter, meaning passenger flight, and also considering the importance of the freight carried in passenger aircraft, not the dedicated freighter aircraft. We are exactly at the same value than ICCT. And if you look at the fuel burn of IEA, we are around at 81.2% of the total kerosene consumption, which is pretty consistent with the values we can find in the literature, looking at the relative importance of the considered perimeter. Now, going down to one level, if we look at the flows, here it's like bilateral flows between two continents, here Asia to Asia, Europe to Europe. The top three flows are within 1.2% of OIG values, while the top 15% are within 12% of error of the OIG reference. And in here in the left, the right corner, we have some kind of minor flows that are very weakly estimated. For instance, Europe to Oceania, we have a 600% overestimation, but investigation on this led us to realize that it was more of a convention problem, because flights, for instance, from London to Sydney, they often have a technical stop in Singapore, for instance. Same for Paris to Papeete, with a stop in Los Angeles. And some datasets consider these two flights, these two legs, as two separate flights, while some other consider them as one single flight. So it's more of a like a convention difference between OAG data and the data we use. Now, if we go at the country level, which is a more refined level, we can see on this map where the yellow is around the same value, blue are overestimation, and red the underestimation, that most what I call data-rich region, such as the North America, Europe, and also Brazil and Australia, are pretty well estimated. And we still have some weak estimation in other countries. The most problematic market is Indonesia, because it's quite an important market for aviation, and we still have a 24% underestimation in this country. Maybe because compared to other countries, it is a country with a lot of island, meaning that everything being equal, otherwise the aircraft will be used more for international, for national flights in these countries than other countries. And in Eastern Europe, we have some kind of overestimation, especially in Turkey, with 17%, while comparison with Eurocontrol source led us to believe that maybe OAG data, and especially the conversion from 2018 to 2019 values in this country, was maybe something insufficient. So it's more also from our validation point of view than in the core datasets that there might be a problem. And something interesting to see is that especially in China and in India, even though these regions, we didn't have any information on them, it's pretty well estimated. So that's something we can really be satisfied with. If we look at the CO2 value still at the country level, this time looking at ICCT data, you can see that for international flights, most of the values are within 10 to minus 10% of ICCT values. So that's very satisfactory. And if we look at the domestic flights, this time we can see a little bias toward underestimation, which could be the effect of the fuel burn, the very simple fuel burn model we've used, being too optimistic on shorter flight than on longer flights. So that might come from this. If we look at the airport level, the conclusions are really the same. The major airports are all in yellow here, meaning that it's well estimated. There's no major airport with a very skewed estimation. And if we look, there's still something that we can say about it. For instance, Liège and Luxembourg airports here are very weakly estimated with a very high overestimation. And looking at the dataset, the core dataset, we saw that it was also linked to the fact that these airports are very big cargo airports, while they are very minor passenger airports. And some flights were included in our dataset labeled as passenger, while they are indeed cargo flights. So that's things that we could work on airport by airport to continue improving the dataset. And finally, at the route level, really that I want to insist on it, that's really not the way we want to use this data. Route per route analysis are not our objective, but we can still look at the R square and the quality of the data on this level. We can see that the dataset here in terms of number of seats and here in terms of number of ASK is relatively unbiased. Each color is a different source we've used in the dataset. We can see that most of the datasets from existing open source are really well correlated. The estimated data is unbiased but quite highly dispersed, and that's something we could have expected. And also, there was a small bias towards underestimation for OpenSky data. Because we've used OpenSky data of 2019 in this work, I guess today with an extended coverage, it will be much better, and that will be very interesting to look at. And the fact that switching from seats to ASK, you can see here, improves the R square, because that means, I think, that the longer flights are better estimated than shorter flights, and that gives more importance to longer flights switching to ASK. Now, we wanted to capitalize on this open source dataset to create an open source tool that allows everyone to look at the different flows of emissions or ASK in the world. And that's what we've done. So you can see this tool that is open source, and you can analyze at different levels, continental level, country level, or route level, even if it's not really the core use case. At the country level, you can just look at the whole world, or zoom on a specific country, such as France in here, and look at the CO2 flows for each destination served from France, and look at various analyses, such as tree map analysis of those flows, to look also at the repartition of flights according to distance or aircraft type or things like that. Now, this tool is open source and will be made available on the server of Sparrow in the upcoming days. For now, it's only available on the GitHub of the project that you can already access looking at Aeromaps Aeroscope GitHub. Now, a few words to end this presentation. Really, going back to the objective and to the aims of this work, was to create an open source, or mostly open source as possible, flight emission database for Aeromaps to enable us to do custom analysis on Aeromaps of decarbonization scenarios. So to do so, we've collected as many open source databases as available. We've used Wikipedia as a way to complete those data, to train a regressor on known routes using features on airport or routes and countries, so that we are able to estimate the traffic on unknown routes from the Wikipedia dataset. As an outcome, we have now global coverage air traffic flow database with an accuracy that we consider as sufficient for aeromaps regionalization, for customizing aeromaps, even in data, what I would call data poor regions such as Asia and South America and also Africa. Not yet for a very detailed route per route analysis, but that's not our core working subject. And we've done also some processing notebooks that allows everyone to access this data and to visualize this data using the dedicated tool. In the upcoming works that could be done on this model, on this work, we could try to improve the models using incremental improvements, such as including additional countries and additional minor datasets into the list of existing datasets. For example, there's a dataset for India that exists, just the format of it is very unusual and very, like it would require a lot of pre-processing of the data to be able to use it in this framework, but it could really improve the estimation in Asia. We could use very much more advanced estimation techniques, such as, for instance, graph neural networks, to try to better capture the fact that the routes are indeed a network and not just a list of unconnected routes. And we could, like the major objective for us now is to adapt aeromaps to be able to handle this database as a starting point, which is not the case yet and will be my work for the next few months. And also this dataset, it could be used for other applications such as sociological study of air transport to know who flies in the world, the number of trips per capita in the world, such as that, and also to, for instance, try to recalibrate some aircraft top level requirements using the existing routes to look at how many flights are done on which distances and things like that. So on these few words on the future prospect for this work, it's time to conclude, and thank you all for listening to my presentation, and I'm ready to answer to any question.
Thank you, Antoine. We have time just for a couple of questions. The next, okay, Xavier. So then we can continue over the break.
Thank you, Antoine, for this presentation. I have a very nasty question for you, because everything was very good. So it just, I'm wondering how relevant such a study can be without including the passenger-centric view, because we have no data about passengers, about the demand for passenger for going from one point to another through a connection hub or not. And that's data that's lacking, I know. But what's your take on this?
Yeah, for at least for perspective, I think that's very relevant to access to this really, like, not focusing on origin and destination, but really on the trip origin and destination, because obviously there's many options to travel from Toulouse to New York by connecting by various hubs, as you said. Just our focus one was on estimating the traffic for a reference year of 2019. And for that, we can just look at the resulting flows and the resulting flights. That was just to have a snapshot of the traffic in 2019 using only open source data. To do prospective and detailed prospective, we really need to model demand. But modeling demand at the route level is something that is very, very complicated. At the country per level, it's something that is possible to do. And what we want to do is really now to start from this 2019 point with this data set and use like regional growth rates to try to project the future's flows of air travel. But we won't be able really to take into account the various evolution possible for networks reconfiguration, for instance, in the upcoming years. That's obviously something that is lacking so far in our work. But
thank you. I just wanted to ask you if you had checked the discrepancies between the OAG and the 2019, the discrepancies that you had. Were they maybe due to the fact that OAG is only planned flights and not the one that actually took off?
I guess I haven't looked at it. Like OAG dataset was made available courtesy of TU Delft, and I really was into using this dataset as a validation.
Okay, so it's like a ground truth. You used it as a ground truth in your case, right?
As a what?
The OAG life.
Yeah, exactly.
Okay.
And therefore, it's and I think OAG also does estimation on their side. I don't think their data is fully like airlines schedule. Some airlines, because I've been discussing with OAG in the beginning with them to see if it was worth buying the data of OAG or not for our use case.
All right.
And in the end, they said that most of their work was to collect airlines schedules and also to estimate the data. So there's also estimation. So it's pretty hard to compare. And even ICCT data, the other validation source, they also use OAG dataset as a schedule reference. So they just take it and put it in their performance model to have the CO2 emission. So without more insight in OAG process, it's very hard to conclude at the country level if their value is right or not. So no real answer on this. Sorry.